about housing. And in fact, Natural Resources Canada, a government department, was so impressed with this house that they started to take a look at the features of it and developed something in 1980 called the R2000 House Program. R2000, has something to do with thermal resistance, right? And 2000, the thinking was all houses are going to be built like this in the year 2000. Didn't quite happen that way, but a lot of good things did come out of the R2000 program. First of all, it set metrics to this idea of reducing air leakage. It set a number on how to measure air leakage in a house, and therefore set the standard. The standard at the time was 1.5 air changes per hour. That would be the leakage. So in other words, every hour, the entire volume of your house changes over 1.5 times. Sounds awful. In Britain, the number is 15. So here you are, paying for fuel 15 times every hour to heat up the air in your house. So if that air doesn't leak out, you're only paying for it once. And that's why air leakage reduces fuel costs. The other thing it did was it defined metrics for universal measurement of energy. It would take a look. It was the first time that we were able to add up the insulation values of the wall, the roof, of the underslab insulation, the U values of the windows, combine that with air leakage and come up with a number which was the theoretical energy consumption of the house. And there have been so many R2000 houses built now, about 12,000, that the computer software program that they use to predict what the energy consumption is going to be is very, very accurate because it's been field tested so many times. The problem is it's old, so they're now replacing it. It's based on a DOS system, so it's getting a little ancient, but it still works. The other thing R2000 did was it identified critical inspection points, and that was something a speaker referred to this morning. What is it that we should check because we can't check everything? And so what we did was we took a look at HACCP. I don't know how many of you have an agricultural or a food background, but HACCP is Hazard Analysis Critical Control Points. It was developed because NASA was sending astronauts up into, for weeks in outer space, and they didn't want them to get sick from food poisoning, so they had to make sure that their foods were absolutely safe. So what they did was they looked at the food processing process and picked out all the points where if you made a mistake, something critical would happen. We do the same thing in R2000/Super E, and that is we only look at the things that if you do them wrong are going to create a disaster. So we look at air tightness. We actually go out and measure it because we know that if you have too much air tightness, the disaster is going to be that you're going to lose a lot of energy and you don't have an energy efficient house. The other disaster is you're checking the quality of the construction, because if you're aiming for 1.5 air changes per hour and you end up with 4, it means the guy who built the house made a mistake. So you got to go back in and look for what mistake he made. We take a look at ventilation. If you don't ventilate the home correctly, the people inside it will get sick. If you don't ventilate an airtight house, you will actually get moisture accumulation enough inside the home to create material damage. You will have deterioration of construction materials. If you have a buildup of humidity inside the house, you got to get rid of the humidity. The only way to do that is to ventilate. We also take a look at, is the ventilation balanced? So we use heat recovery ventilators. They blow exhaust stale air out and they bring fresh air in at the same time. They use the heat from the air going out to warm up the air coming in, which is what makes it energy efficient ventilation. So you got to make sure that you're sucking as much as you're blowing. Because if you don't, you'll either overpressurize the house or you'll depressurize the house, and that will increase air leakage because there's greater pressure for the air to leak out of the house or in the house, depending on whether it's overpressurized or underpressurized. The other thing that we look at is wall structures. So I want to see a cross-section of this wall because we have to determine whether there's any place inside that wall where moisture will accumulate either from uncontrolled air leakage or from vapor diffusion. So if I put the vapor barrier on the cold side of the wall, there's going to be condensation occurring inside the wall that's going to lead to mold growth and building material damage, and we don't want that. So that's our hazard analysis critical control points. So it's the only things I really have to check to tell you whether you have a good house or not. So that's what R2000 calls for. It also clarified, R2000 did, what this whole house as a system stuff is. Put it all into a course material, rolled it out as a national training program, which was delivered by ESCOs, by the way. And so we trained hundreds, if not thousands, of builders across Canada about house as a system. So there's sort of this, or was in 1980, this basis of knowledge among the construction industry about what makes a good house and what doesn't make a good house. So that was 1980 when we rolled out R2000. It is still in existence. They have upgraded the standard several times and is due to be upgraded again this year. From R2000, a lot of people took notice. In 1990, for example, the Passive House program was developed in Austria and Germany, which is basically house as a system. They measure the energy consumption a little bit different. They set their air tightness levels a little bit lower, but it's basically the same thing. It's airtight, ventilate right. In 1999, along came my program, the Super E program, which is essentially R2000 for export. We went to Japan first because they were very interested in energy security because they kept building nuclear plants on seismic zones. And they didn't want to do that anymore, so they wanted to cut their reliance on foreign energy and nuclear energy. And in 2007, it begat the Equilibrium program, which is a contest which was run by Canada Mortgage and Housing Corporation, which is Canada's national housing agency, challenging the building industry to come up with a house that used no net energy. And we built 14 of them across Canada. I think I have a picture of the people. Somebody was talking about zero energy this morning. Most of these are zero energy or near zero energy. A couple of them are positive energy. They're actually feeding energy onto the grid beyond what they're using. So what equilibrium means, it's more than just energy, but it does mean net zero site energy, which means we have to have the smart grid. So during the daytime, nobody's home, the solar panels are raging away, they're feeding electricity back onto the grid. The meter measures how much goes onto the grid, and we are allowed to take that back at nighttime, as long as over the course of a year, we're not taking on more than we're putting back onto the grid. There are some environmentally sustainable measures which are included in equilibrium, and we demand a healthy indoor environment, which means ventilation. There's a picture of 3 of them. Yes, it does. This one in the middle here is in Ottawa. This is the one that is positive energy. Someone pointed out this morning, I think when they were talking about passive houses, that it's very difficult to build a passive house in a cold climate. I assure you, Ottawa is colder than any place here, and it is positive energy. This one over here is one in Quebec, which is using a number of very interesting technologies, including ground source heat pumps, and it has a very cool PV roof. The entire roof is PV. Part of the criteria for the equilibrium program was we had to include a clothes dryer. We couldn't say, no, you can't have a clothes dryer, you just hang your laundry on the line. No, you've got to put a clothes dryer in. That takes up a lot of energy. So what we're doing is we sealed the airspace, and I say we because I was on the design team. We closed the airspace behind the PV. And so it gets very, very hot behind the photovoltaic panel in this airspace. So when we want to use the clothes dryer, we evacuate that airspace and use it to dry the clothes. It's very cool. It cools down the PV panels so that the lifespan of the PV panels is longer. This other one, the third one here, I believe is just about exactly zero energy, and I'm going to talk a little bit more about it in a minute or two because it is a retrofit. So we've got 14 of these things going on. In my other life, I manage a program for the Asia-Pacific Partnership that builds zero energy projects around the Pacific Rim. And in every single case where we have a zero energy house, it has these traits in common. Very airtight construction, extremely well insulated. There is mechanical whole house ventilation with heat recovery, energy efficient appliances, and then and only then do you put appropriate renewable energy on it. I was at one in Korea. They wanted to retrofit a school. It's an orphanage, actually. And they said, we want to show it to you. You tell us what you think. And I think what they did was they ran out and they looked up renewable energy sources in the dictionary, and everything it said there they put on this thing. Oh, they had geothermal heat pumps. They had PV systems. They had solar thermal. They had windmills. They had everything you could imagine. He said, what do you think? I said, can the geothermal system and put in some insulation? So you need to go through all of these other things before you get to renewable energy. All of the successful ones also follow the house as a system. And it takes me about an hour and 15 minutes to explain house as a system, so I'm going to see if I can do it in 30 seconds. First of all, you reduce heat loss in the building by adding insulation. If you add insulation, there's only three kinds of insulation. There's foil, there's foam, and there's fiber. In the case of foil and foam, you actually have to affix it to the wall in order for it to work. Because if it's flapping around in the breeze, it's not working. Because you're affixing it to the wall and you can't breathe through it, you have automatically changed the airtightness properties of the building. With fiber, it's not the fiber that insulates. It's the air the fiber is holding that insulates. So if you're allowing wind to blow through the fiber, you have no insulation. Therefore, the mere fact that you have added insulation means that you have changed the airtightness properties of the building. So, if you still don't know where the building is leaking and you're concentrating the spots where that leakage is occurring, warm air carries moisture. And so when that warm air is leaking through that hole that you have left, eventually, as it's going to the outside, it's going to cool down, and it's going to cool down enough to condense, and it will dump a load of water in your walls. So you have to stop it. Therefore, you insulate, you have to make the building airtight. Well, you have appliances in your house. If it's in Canada, it's a forced air furnace. Here, it may be a gas boiler that require combustion air. If it's got a flame, it needs oxygen. It's going to take that oxygen from your air, which means you have to worry about combustion air. So you either direct vent, or you have to worry about some kind of ventilation system. Plus, you have people in the house who have to breathe. And if it's airtight, you're going to trap a lot of pollutants in the house and people are going to get sick. So you have to ventilate. And all that stuff I said about warm air carrying moisture and condensing, you need to understand how air flows, how heat flows, and how moisture flows inside your house. Put all that stuff together and you've got house as a system. There you go, that took about a minute. The house as a system is a very powerful tool. I have not yet come across something that is happening to a house that cannot be explained by house as a system. It answers everything because it is a science. And we can apply the theories of house as a system to just about any circumstance to explain what is happening in the house. And you have to understand it if you're going to try energy retrofits. And somebody said this morning, there's 12 million square meters in standing residential in Latvia. That 12 million square meters is going to have to be addressed, and you're going to have to go back and retrofit it for energy efficiency someday. If you don't understand house as a system, you are going to be creating problems because you are going to change the airtightness properties of all of those buildings. And if you don't know what you're doing, you're going to get moisture damage and you're going to get mold. So house as a system is the first step on the road to zero energy that works. Okay, here's some retrofit. Now I'm talking about retrofit. This is a 60-year-old wood frame house in Toronto. It is about 112 square meters. Toronto's pretty cold. It's about like here. Our design temperatures for January are minus 22 Celsius, and in July, plus 31. So it's quite a temperature range, just like you get here. And this was one of the equilibrium homes It did hit zero energy, so the energy consumption is 0 kilowatt hours per square meter per year.